All right, everybody, let's get started. Couple quick announcement items. So I checked the grade book, and my TAs are chipping away at the homework 6s. So 6-1 to 6-2 are graded, so the trust assignments are graded. The shear and moment diagram assignments, they are still working on, but the solution should be posted for all of those. Probably by the time that you come back from break, everything will be graded other than homework 7, because homework 7's due Wednesday after break. But that's it. That is our last homework assignment in Engineering 213, is homework 7. I posted an online lecture that went live on Friday. That one was more about concepts involving friction. Now, if you wanted, you could go ahead and start tackling homework 7 now. But on Monday, when we come back from break, I'm going to go through and start looking at how friction problems change if you start adding some trig to it, if you start having objects, on an incline. And so that was sort of the idea, is that I would split that up into one lecture that just goes through the concepts and then one that goes through a little bit more of the details. Okay, so that's due Wednesday after break. Today, as you know, we are reviewing for our exam. So again, today we're doing exam review. Wednesday we celebrate, and on Friday we don't have any class, unless you all want to have class at 8 a.m. the Friday before Thanksgiving break. It's like the whole time, it's like trying to get feedback, everybody. But when I say let's meet Friday at 8 a.m. before break, suddenly everybody gets vocal. So, if anything, it'll save you another cold walk from engineering to Corbally, right? We don't have many of those left, so maybe that's something to look forward to. Okay, exam review time. So let's go through the logistics, the materials, format, and all that. So first off, this is not any different than any of the other exams that we've had in here. You can expect 4 to 5 conceptual questions and 2 to 3 computational problems. Again, it's not intended to be time critical. So I do the exam myself, and if I can do it in 15 minutes, you should be able to do it in 45 minutes. So yeah, we are going to do it in here in person. It's closed book, closed notes. You are allowed a formula sheet. I would say on this exam, more than any other, bring a straight edge, okay? Because as you know, there is the construction of shear and moment diagrams. We have the computation of centroids, which might need you to draw a table or something like that. So have a straight edge on this exam more than any of the others. I think it would definitely make your life a little easier, okay? Now, I want to make sure, and I'm really hammering this in about formula sheets, because we had a couple students on the last exam that didn't quite follow this, and I didn't really make a big deal out of it, but I really want to enforce this now. So again, you can bring a formula sheet. You can put whatever you want on it with the following stipulations, and the last one is the one I really want to talk about here. But first off, make sure you have your name on it, because I'm going to collect them all after the exam. You do not need to copy down necessary property tables, and so I'll show you what I mean by that here in a second. So for example, this table I'm giving you on the exam. I'm giving it to you. So you do not need to waste time on your formula sheet with this, because I'm actually giving you this table on the last page of the exam. Don't include any fully worked out problems. That really wasn't a big deal, but this last one is probably the one I really want to focus on. I want you to make the formula sheet. We had a few of you that just took the slides, snapped them into a Word document and hit print. It needs to be prepared by you. I don't care if you word process it. I don't care if you snap an image here and there from the slideshow, but actually take the time and make it, synthesize the information into something that makes sense for you. Okay, let's talk about the topics on the exam. Okay, so really, this is it. This is it in a nutshell. Again, as I mentioned, my exams are not intended, the first 3 exams in the class are not intended to be comprehensive. I mean, in order to solve a truss or in order to draw a shear and moment diagram, you do need to be able to compute support reactions, and I know that was on a previous exam. There's no real way of getting around that. But I'm not going through particle statics or R cross F or anything like that, because we haven't talked about that since the second exam. What I want you to be able to do on this exam, first off, let's talk about centroid. So make sure that you can locate the centroid of a line, an area, or a volume. That's pretty much it in a nutshell. And make sure that you can compute the moment of inertia. Okay, if you can do those two, you're rocking and rolling. You're good to go. I'll go ahead and tell you, because I'm sure I'll get this question during the review session. I am not going to make you break out the integrals and start deriving formulas for shapes. I'm not going to make you do that. Okay, so don't worry about that. All right. That doesn't mean that you don't need to be able to use the references that you see here, but I'm not going to make you do the calculus-based derivation. I'll go ahead and tell you right now. I'm not going to worry about it. The other main topic that we've been talking about for the past few lectures is the analysis of structures. And we've really been focused on two classes of structures in here. The first are trusses and the second are beams. Now for either of those, you do need to be able to compute support reactions. You can't analyze a truss or draw a shear and moment diagram without being able to compute a support reaction. So you do need to be able to do that. But for trusses, you need to be able to compute the internal member forces in a truss using either the method of joints or the method of sections. Okay, there are reasons why one method is more appropriate than the other, and you should know when one method is more appropriate. Largely, method of joints is tedious, but it'll get you the answer everywhere, whereas the method of sections will get you an answer at a particular member, right? So just make sure that you're cognizant of those reasons. And finally, be able to draw shear and moment diagrams. If you can do all that, you're good on exam 3. Now, in terms of the concepts, we do know that, so, I am going to ask you conceptual questions. Make sure that you understand that, if we integrate a region, we get an area, but if we integrate x times a region, that is the first moment of area, or x squared, that's the second moment of area, and so on and so forth. The second moment of area has a very special name. We call that the moment of inertia. And so remember the subscripts are flipped. That's not a mistake. That's on purpose because the distance from the x-axis is called y. The distance from the y-axis is called x. The first moment of area is useful in computing the location of the centroid because if you take this integral and divide it by the area, that tells you where x bar is. You do need to be able to use these. Okay, so I'm going to give you this right here. I'm giving you this on the exam. This table right here. So it's the last page on the exam. This list isn't complete. You have a more comprehensive list in your textbook and in the FE reference manual, but I'll go ahead and tell you, you're not going to get asked any centroid questions beyond what's on this. I do not want you to waste time on your formula sheet littering it with stuff like this and stuff like this. Any of these formulas that you need, you will have. Okay, point blank. All right. So, but you do need to make sure that you understand how to use them, and by use them, I mean understand how to compute the centroid of an area, or the centroid of a volume, or the centroid of a line segment. You do need to be able to compute the moment of inertia of a composite shape, and so in order to do that, we utilize the parallel axis theorem. And so the parallel axis theorem states if I want the moment of inertia of a composite shape, I sum up these terms for all the simple shapes, and these terms are the centroidal moment of inertia of each simple shape plus AD squared. A being the area of that shape, and D being the distance from the centroid of that simple shape to the centroid of the whole thing. And that one's really easy to compute because you just take y minus y bar for the shape in question. So it's just a big algorithm. It's not. I don't think it should be that difficult. Just takes a little bit of time. Okay, and if you need these, I will give you these as well. I have the page. There's a page in the back of the exam that has a host of reference formulas like that you'll need on the exam. Okay, for truss analysis, we have the method of joints and we have the method of sections. The method of joints is a concurrent force system problem. That means all the forces all meet at a common point. So what that means is that you're only afforded two equations of equilibrium when you're assessing a joint. So when you're analyzing a joint, you can only solve joints where there are at most two unknowns. Whereas with the method of sections, you can cut a section through a section that has at most three unknown member forces. Because now we have a non-concurrent force system, and that non-concurrent force system means that we have a third equation of equilibrium we can utilize in order to solve these members. Again, the method of sections is a little bit more advantageous for spot checking or for analyzing or determining forces in a given member, whereas the method of joints will help you out with the whole truss. Finally, we have our shear and moment relationships. So we know that the relationship between load, shears, and moments can be defined from a differential or integral basis. So if I have the load diagram, and I integrate that load diagram, I get the shear diagram. And if I have the shear diagram and I integrate that, I get the moment diagram. But probably what's more useful to us as engineers are sort of the conclusions for our graphical approach. So when we have our load diagram, the first thing that we need to do is construct the shear diagram. And we know that at any given point, the slope on the shear diagram is equal to whatever the load is. So if we have a beam with a bunch of point loads on it, the shear diagram just looks like a big stair step because between the point loads, there is no load. So the slope of the shear diagram is 0. That's why it's just a bunch of horizontal lines like a stair step. Now, between 2 points, the change in shear is equal to the magnitude of load between those 2 points. That's another reason why we had a stair step approach for a bunch of point loads, because between those two loads, or between those 2 point loads, there's nothing on the beam, so there's no change in the shear. Now, between shear and moment, what you got to do is you got to integrate the shear diagram to construct the moment diagram. And for the beams that we're looking at in here, largely we're just using a graphical approach. So our shear diagram is just a bunch of rectangles and triangles and maybe some trapezoids. So we don't need to break out the integrals in order to compute the area under the shear diagram because the shapes are pretty easy. Now keep in mind, you know that the slope of the moment diagram is equal to the shear at any given point, and that between any 2 points, the change in moment is the area of the shear diagram. So that's where we had derived these sort of graphical relationships. This is what we have for concentrated forces. So whenever you're drawing the shear and moment diagram and you have a concentrated force, what that concentrated force is going to do is it's going to cause a jump in your shear diagram. So you had a shear here and you jump to another shear, and the magnitude of that jump is equal to the magnitude of that load. You have 2 shear diagram regions of 0 slope because there's no load here, so there's no slope here. But we have a constant shear here and here, so a constant slope here and here. That's why we go from constant to linear. And that's why we have a slope change right there where the load is, because we have a value change on the shear diagram. For distributed loads, we go one level higher. So if we go from load to constant to linear, now we go from load to linear to parabolic. Okay? So we have our constant load, and that constant value determines the constant slope of the shear diagram. So we have a linear shear diagram. We go from a high shear region to a low shear region in this example. So we go from a high slope region to a low slope region on the moment diagram. And that total change in moment between those 2 points is equal to the area under the moment diagram curve. And that's exam 3. Okay, so with that, I'm going to stop for a sec and see if you all have any questions. I made a post on Teams yesterday, and I said, come prepared with questions. So with that, the floor is yours. What questions do you have for exam 3? Are you ready to just get this thing over with? Are a lot of people ready to do that? Let me ask you this. Is there any one topic of these 3 that you feel least unsure about? Trusses, beams, or centroids? Which one are you feeling the most fuzzy about? I'm curious. And if so, why? Are we all feeling good? I'm okay with that if y'all are. If we don't have any questions, we can end early, but I want to make sure you all are getting your money's worth. So, yes.
All right, so if we have to do analysis with trusses, are you going to give us one that is just, I'm assuming you're not, but...
It'll have 857 members in it.
All right. Is he joking?
Yes, I am joking. I'm just... No, listen. Okay, you only have 50 minutes. Okay, I'm not interested in turning this into a time crunch exam. I'm not. Okay, I'm telling you that this exam is well within the ability to be completed in 50 minutes, okay? Now, what I hear, okay, so to answer your question, let me answer it this way. I'm not going to give you some trust with a ridiculous number of members and say, give me the forces and all those members, because that's just going to take a long time, okay? And there becomes a point when it stops becoming an examination of your ability to solve trusses, and it starts becoming an examination of how fast you can write things down and how fast you can hit buttons on your calculator. I've never been a fan of that, okay? Now, let me qualify that statement with a couple of points, okay? It is possible, just living in the land you're talking about, it is entirely possible that I give you a truss with a ridiculous number of members, and I say, give me the force in that member, okay? But then it's up to you to recognize that if I give you this monstrous truss and I only want the force in one member, use the method of sections. It's a lot faster, right? That's on you, right? So if you have a scenario like that, that doesn't make it a long problem. Okay? It's actually short. It just might look terrifying. Does that make sense? But that's sort of like on you to recognize what method is most appropriate. Okay? Did that answer your question? All right, how about everybody else? Everybody else okay with that? Like, I know that the method of, I know that truss analysis can be tedious. I'm aware of that, which is why I've crafted the exam in such a way that it shouldn't be that tedious for you if you know what you're doing. Good? How about everybody else? Everybody's quiet. If you got here and went, oh, we have exam review, I forgot. Okay, we had one that was honest. I like that. Let me ask you a question, because I want to make sure that your time's being spent valuably. Okay, would you all? The one question I got was a question about trusses. Is trusses the one thing that you all are worried about? You're shaking your head no. What about you?
Probably centroids.
Centroids? Okay, so before we go on trusses, tell me what's your main question about centroids.
Well, in Calc 2, when we were doing centroids here, we were doing centroids in Calc 2, and for me, I was just kind of like lost between how long it takes for Calc 2 and how much more different we do it here.
Well, what I can tell you is we are not going to be using any integration. So here's what I'll tell you, okay? All right, when it comes to centroids, we had 4 homework assignments on centroids. 5.1 to 5.4. 5.5 was the homework on moment of inertia. So if we're just talking about centroids, when you're studying, ignore 5.1. Because 5.1 was the one where I gave you the region and I said, derive the formula for the centroid. That was probably one that was more aligned with what you did in Calculus 2. And I'm not interested in you all deriving that for the very reason that you do that in other classes like calculus. You know, I'm trying to go into a more applied region, if that makes any sense. That answer your question? Are you feeling better? How about everybody else? So let me ask you this. Other than that, is trusses the one-ish thing everybody's worried about? So I have an idea, okay, because everybody's being kind of quiet. We can do this one of two ways. We could end class early, and I have no problem with that, or we can do a truss problem right now. Would you like to do one? I have one ready. If you'd like to. You want to do a truss problem? Let's do a truss problem. That way you're getting your money's worth. And I'm going to show you, I don't want to say another way of looking at it, but maybe this is a cut for difficult problems that look scary. Okay? So All right. Okay. So I have a truss here that looks like this, and we're going to say that that's 5 feet, okay? We're going to say that this is 12 feet. All right? And this truss has 10 kips of applied load on these two joints. And the answer, or the question, is to solve the truss. Okay? So first thing I'm going to do is I'm going to move this over a little bit. So we're going to solve this truss. And I'm going to show you maybe a different way. So let me be clear. I don't think this is all that different. I think we're going to be using the method of joints like we did before, but maybe a way of organizing it a little differently. I don't know. So what we're going to do is we're going to solve this truss. Now, this truss is cantilevered, right? So we've got reactions that are going this way and up and down. Now, what I'm going to do first off is I'm going to recognize the direction of my reactions, okay? Because this is cantilevered, the order in which we solve for our reactions is going to be a little different, okay? So I'm going to call this EY, and what I'm going to do is I'm going to call this EX, and I'm going to call this AX, okay? Now, I want to say something right now, okay? If you look at this truss and you see, okay, the only unknowns in the horizontal are these two, so they must be 0, I want you to stick out your hand and do that, because that's wrong, okay? These two do not equal 0. Their sum equals 0, okay? They could very easily have value, and in fact, they do in this problem. But I'll show you what I mean here in a second. Now, going back to my equations of equilibrium, the first thing we need to do is compute support reactions. Which one do I compute first? Well, how many unknowns do I have in the horizontal direction? How many unknowns do I have in the vertical? Why don't I sum forces in the vertical direction first? So we have EY going up, 10 down, 10 down. I get that. Now, some of you are probably thinking, as we're going through this, how in the heck did Dr. Mike look at these reactions and see that one's going left and one's going right? You're going to see here in a second. Again, you could assume they're both in the same direction and just let the math work itself out. There's no magic to getting the assumptions right or wrong. It doesn't really matter, okay? Now, I'm going to let you drive the train a little bit. You tell me what to do next. I have some forces in the y direction. Now what do? Some moments. Where would you like me to sum moments? E. Let's sum moments at E. We have two reactions going right through joint E. It's going to make our life a little easier. So let's sum moments at E. All right. So let's sum moments at E, okay? Do I need to consider EX or EY? No, okay? What about AX? Does AX contribute moment to E? Yes, okay? In what direction? Is this positive moment or negative moment? Positive. And what is my moment arm from E? 10 feet, okay. So plus AX times 10 feet. Let me erase that. All right. What about these two? Did they generate positive moment or negative moment at E? Negative moment, okay? So it's going to be negative 10 kips times something and negative 10 kips times something. So negative 10 kips times something minus 10 kips times something. What are those moment arms from E? How far is it from E to the line of action of this force? 12 feet. And for this one, it's what? 24. So AX times 10 feet minus 120 minus 240 equals 0. So AX times 10 feet equals 360. So that's going to be 36 kips to the right. And if this is 36 kips to the right, what is that? 36 to the left. So what I'll do is that, and then we have that pointing to the left because we made an assumption that EX was pointing to the left and we got a positive answer. Okay? So let me write that up here. Okay. Now I'm going to take a second before we move on. I want to make sure this part makes sense. Okay? I don't want this to be an area of confusion on the exam. And I don't care if it's trusses, I don't care if it's beams, what have you. You need to be able to compute the support reactions of a structure. Okay? Is there anything about this that was confusing? Okay with this? All right. Now, before we move on to actually doing the method of joints, I want to make sure, is everybody okay with identifying that these diagonals are at a 12 to 5 slope ratio? Is everybody okay with that? Now, just for sake of discussion, if this is 5 and that's 12, anybody know what the hypotenuse is? 13. This is a 5, 12, 13 triangle. 5, 12, 13s are special, just like 3, 4, 5s. 8, 15, and 17. That's another one. So, in fact, all of these are at 5 to 12 slope ratios. Okay? Does that make sense? All right. Now, I'm going to give this a sec because I'm going to scroll down here in a bit. Before I do, does everybody have this drawn out? Okay. Hold on. There we go. That's a little better. I needed something on the screen for it to want me to scroll down. Pen cord doesn't like me. All right. Now, what I'm going to do for the method of joints for this truss is I'm going to try and do it all at once. Okay? And this might be a way of making these problems a little easier for you, okay? Let me explain what I mean. Let's do that, that. So what I've got is I've sort of got the entire truss drawn out right here. And I'm going to sort of do this. How many of you thought when you decided to major in engineering that there'd be so much drawing? That was a joke, not very funny. Okay. All right. So what I've got is I've got the entire truss drawn out, but I kind of exploded it a little bit. Okay. Now what I'm going to do is I'm going to take a second and draw the forces that I know. Okay. So I know that this is 10 kips. Okay. This is 10 kips. I know that this is 20 kips. I know that this is 36 kips, and I know that this is 36 kips. Okay? Now, all of my diagonals are at a 5 to 12. Okay? So let's see if we can start solving some members or solving some joints. Okay. Can I go ahead and solve this joint right now? No, why? There's too many unknowns, right? I've got 4 members, right? So if I start labeling these, let's put some letters on this so we can kind of speak the same language. So this is A, B, C, D, and E. There's only 2 joints I can start with right now. Which ones are they? I could start with joint C. What's another one I can start with? Sorry. Well, I can't start with A. A has 1, 2, 3 members, right? I could start here or here. This kind of seems easier. I don't know about you. I'm kind of lazy. So let's do this one first. Okay? So let's put my members. Put my member. So there's my members. All right. So if I've got 10 down, what does that mean? 10 down means I got to have how much going up? 10 up, right? This diagonal here is going to have a horizontal and vertical component, so that's got to be 10. Now, if I have a vertical component, I can immediately go through and determine the horizontal component, right? These members are at a 5 to 12 slope ratio. So the x component is to 12 as the y component is to 5, right, for all of these truss members. So what that means is if I have the vertical component, the x component is 12/5 of the y component, or the y component is 5/12 of the x component. In other words, in this case, the horizontal component should be larger. So if this is 10 kips, what is that? Break out the Casio FX115 ES Plus or similar scientific calculator and tell me what that is right here. Say it again. 24. Which way is it pointing? To the left or to the right? To the left, right? Remember, you have a diagonal member, either they both point away or they both point towards, okay? All right, so looking at this joint, what is that? What is this horizontal member? Member BC. 24 kips to the right. There you go. All right. Now, before we do any other calculations, I want to see if this makes sense. Everybody good so far? Now, here's what's new. I'm going to use this to track the entire truss. So watch this. Let's look at the horizontal member BC. If this is 24 kips to the right over here, that means whenever I decide to do this joint, that's 24 kips to the left. Remember, on the other joint, you flip the direction. Same thing with this member right here, okay? Whenever I decide to solve this joint, I know that this is 24 and that is 10. Make sense? Okay. Let me ask you this. Can I solve joint D right now? You tell me. This is joint D. You said no. Why'd you say no? 3 unknowns. Well, what about joint B? Can I solve this one? Yes.
On joint B, why didn't we flip the directions of 24?
Oh, because I did it incorrectly. Okay, that's why. It's exactly why. I screwed up. We'll add a quarter to the mistake counter. You're right. That is supposed to be down like that. Because I must have gotten decaf this morning. That's why. You're 100% right. Yeah. This is 10 up. So that's 10 down. That's 10 to the left, 10 to the right. Whoops. Let's see. Did I get BC right yet? Can we go ahead and solve for joint B?
Yes.
Yeah, because we only have 2 unknowns. All we've got is this member and this member. Joint B is really easy, isn't it? Because if I have 10 kips going down, what's this? 10 up, and what about this one? It's 24. What direction? There we go. So this so now let's go ahead and transfer these. And this time I'm going to get my signs right. I'm going to not blame my coffee this time. So this vertical member, if that's 10 up, 10 down, okay? And this AB, I know that member, $24 going this way. Okay? All right, now, before we move on, I want to take a step back and see, does everybody kind of understand what I'm doing so far? Is this making it maybe a little less tedious? That we're kind of doing it all at once? Kind of like a puzzle, isn't it? A big puzzle. Okay, now, can we theoretically go ahead and solve joint A? Could we theoretically solve joint E? What about joint D? Could we go ahead and solve joint D? Theoretically, yes. Okay? I want to give you a word of warning, though. I would avoid trying to do this joint right now. The reason why is because this joint has two diagonals, and if you have a joint with two diagonals, you're going to end up having two equations, two unknowns, and you're going to have to use your 2x2 equation solver. I would try and avoid that if at all possible. So honestly, I would probably go to either joint A or joint E, because we don't need to solve joint D right now. So help me out. Which joint would you like to do, A or E? Just pick one. A. All right, let's do A. Okay? So joint A says we've got that member right here, that member right here. We have a vertical component here, vertical and horizontal. So tell me which one to deal with first, the verticals or the horizontal. Tell me what to do. Which should I solve for first? Horizontal. So what is it? I got 36 going this way, 24 going this way. What is that? 12 kips to the left. Kips to the left. Now, if that's 12 kips to the left, which way is the vertical component facing? Up or down? Down. And how much is it? 5. 5 kips. And if that's 5 down, that makes this 5 up, doesn't it? All right. Now let's transfer these to our other joints. Wait. Oops, sorry. Didn't mean to do that one just yet. Okay. Now, which joint would you like to look at? E or D? Doesn't matter. Say it again. I didn't hear it. Somebody pick one. E. All right, let's do E. Okay. Now what happens at joint E is kind of cool because we only have one member that we're solving for. Let's solve for each of these independently. Let's deal with the x-axis. So if I got 36 to the left, that means I've got to have 36 to the right. And if I have 20 up and 5 down, I need another 15 going down, right? But watch this. What is 36 divided by 15? 12 over 5. Independently managing each of these, they align with the slope ratio. So it's a check that what you're doing is correct. Also, looking at each of these independently, we found that this is to the right and this is down. It wouldn't make a lot of sense if we had one going to the right and one going up. Like that wouldn't make sense. They both either have to align with tension or they both have to align with compression. And they did. Okay. Now, if you really want to get fancy, if you go to joint D and you say, okay, let's take a look at joint D. So at joint D, we have this 36, this 15. Just take a look at joint D. What do we got going on? Let's talk about horizontally. 36 to the left, 12, 24, 36 to the right. Okay. What about vertical? 15 and 5 going up, 10 and 10 going down. 20 up, 20 down. 36 left, 36 right. So that joint is in equilibrium. Okay? And then, now that we have the entire truss right here, we can handle this final answer really easily. Okay? So check this out. Let's look at this member. Is this member in compression or tension? Say it again. No. Both of these forces are going to the joint. You have a bar in your hand and you're pressing it. The bar is pressing against you, right? Right? Here's the truss member. Here's my hands, right? I'm pushing it in compression. The bar is pushing towards the joint, towards the joint. That member's in compression. Does that make sense? Does that make sense? That member's 24 kips in compression. Okay? This member right here, also. $24 kips in compression. What about this member right here? What about that member? You have a bar and you pull it in tension, the bar is wanting to spring back. This is in tension. What about this member? That's 5 kips in tension. What about these diagonals? What do I need to do for these diagonals? Pythagorean theorem. Now what about member AD? I think I can do that one in my head. That's 12 and 5, so that's going to make that 13. Is member AD in compression or tension? Compression. So ahead of myself. What about this member up here? Member DE. What is that? What's the magnitude going to be? 39. Do I have a second on that? All right, 39 kips. Tension or compression? Tension. All right. And I'm curious if anybody can do a little bit of mental math and tell me what this one's going to be. And that one's also in tension. Boom, truss solved. That's a long truss, I'll level with you. And I took probably but another thing I mentioned, I took longer than I would probably do myself because I'm sitting here explaining it to you. But this is basically the same process as the method of joints. I'm just doing it all in one space as opposed to segregating it. It also might be a little easier to track the arrows because they're all there. I also tried to be pretty color coordinated that with any joint, the red forces were the ones that I knew going into it, and the blue forces were the unknowns before we started. Does that make you feel better for the... Keep in mind, this is also in the class notebook as well, so it's under exam 3 review. All right, everybody, I'm going to pull out the code again. I will see you all on Wednesday. Best of luck.